The application demands are increasing something like this. It's almost linear at the very minimum, because as we are trying to work on more and more complex problems, especially if you consider the fields like computational fluid dynamics or ab initio molecular dynamical computations, the requirement varies as the cube of the number of atoms, molecules that you are going to simulate. Okay. At the very minimum, it should be linear. It should be something like this. Okay. But then, what we need to do is that we need to meet our application demands. So the emphasis of us is to meet the application demands. But then this has been tried out by very expensive propositions, as what was proposed by Seymour Cray. Task here is plowing a field. If you are asked to plow a field, you would probably use a pair of handsome oxen rather than going for hundreds of chickens. But then you go in for all sorts of grandeur in terms of using your gallium arsenide semiconductors, very specialized cooling systems, vector processors, and also you have solid state storage devices in terms of your solid state memories. But then this is a very expensive proposition. But then it would be nice to leverage onto the increase in the communication space that one has obtained, and then interconnect a number of processes over the network, and then use a clever piece of software, okay, to do the orchestration of splitting your job, assigning your task to the different processes, and then gathering your results over the network. And this has come to be known as parallel processing. So what we have landed up with from there over to here. Okay. So the application demands have been met by using a large number of chickens here. Now the point to be noted here is that parallel processing was considered to be a panacea, in the sense that okay, you have got a large number of processes to do the job, and the network speeds are increasing. But unfortunately, we have hit up what is known as the power barrier, meaning at higher frequencies we do have the problems leakage currents. And then way back in 2003, Semiconductor Industry Association predicted that there would be 10 gigahertz transistors by 2006. Obviously this has not happened because of these challenges here. Okay, you have the problems of dynamic leakage, dynamic capacitance effects, and then how exactly we are going to address this, because at the end of the day, it's the economy that drives any industry. Okay, now the drive is towards saving electrical power, because we have really hit the power barrier. Okay. So what has been observed over here is that if you really reduce your frequency by around 2 units of 200 megahertz, what you are going to achieve is 40% savings in your power. But then you have a large number of transistors which are already on. Now what is it you are going to do with that? So what guys have come out with is that either the dual core or multi-core processors, you are going to have the larger number of cores over a die, and then you are going to use them. So essentially you are going to reduce the frequencies, and then you are going to have multiple cores. That's what the industry is going all about. Okay. Well, you have multiple number of cores on a given die, and then your chicken have become a little more fatter in terms of the number of cores, and then the fact remains that you need to connect a large number of processor boxes to achieve the speeds or the parallel processing that you need to do with a large number of processor cores instead of having individual processors. Nevertheless, you need to do this. Now, what are the issues, okay, in high performance computing? First thing is you need to provide electrical power. The typical box having a quad-core processor would require around 800 watts of electrical power, and you are going to stack around 1000 of them. You will be needing almost a megawatt of electrical power. From where is it you are going to get this from? And then unfortunately all your computer systems, they don't really have any ways and means of really dissipating the energy that you're going to put in. Everything is coming over as heat, which you need to remove them. And then, of course, as I told you, you have heat up what is known as a power block. So you need to have multiple number of cores. But then for people like us, the free lunch has stopped. Meaning, earlier what we used to do is we had to pour the programs onto a faster processor, and then we did a good job of it. We didn't have to do much, not really much. But then now we need to do multi-threaded programs to exploit the number of cores that are already present. Okay. So we thought that we were smart, and then we wanted to try to solve the problems by having large number of processors and then interconnecting over a network. But then, as what always happens in life, when you try to solve some problem, we are going to introduce many more problems. You just see how that. So how is it you're going to provide electrical power for this large cluster that we are going to make? That requires different administrative domains, because obviously even in a city like in Mumbai, you cannot really have a megawatt of power for any application you need. Okay, so you need to have the collaboration, and then possibly it will be nicer to have a smaller clusters placed geographically apart, and then they are operational. Okay, either it can be geographically separated, or you need to have different administrative domains, which involves a lot of funding issues. And then, as I told you, you need to do the heat removal of these systems. See, we are going to stack these boxes one above the other. Heat removal is different from creating heat densities. Okay. Now, the ideal thing for this would be to have individual boxes spread across geographically different isolated locations. So, removing heat density itself is a major issue. So, ideal solution for this would be to have the geographical separation. And of course, the owning cost, of course, if you are going to build a large cluster, okay, the owning and operating cost of this cluster for about 3 years would be much more than the cost of the cluster itself. So, you need to go in for different administrative domains here. Of course, even if you build a large cluster, what happens is the demands of this would be burst in nature. Okay, you should be able to get the computation power whenever you need it. Should be able to give away whenever you don't. But then, especially high-end systems, you don't really get neither for love nor for money. You need to have the collaborative agreements, especially with the high-end computing systems. So, you need to have collaboration. Redundancy, in the sense that it's always nice to not to put all your eggs in a given basket. So, if should something happen to a given computing center, you should be able to have your operations going on. So, it's always nice to distribute across. Okay. You need to have geographical distribution. So, now, building up large clusters had produced some problems. Now, you try to find some solution. Okay. Now, grid computing has come about as a manifestation of the solutions for the problems solutions found for the problems that are posed by building up large clusters. Okay. Now, the definition forms distributed computing, which enables collaborative sharing of geographically distributed resources. Now you understand why you need collaboration, why you need geographical separation, why you need different administrative domains. Okay. Another constituent component here is the network. Okay. Fortunately, network technologies are not very, very old. It's hardly 50-year-old. Okay. Now we can really trace as the salient points or the kickoff points in the network evolution. Okay. So way back we had what was known as circuit switch networks, meaning you need to have the electrical connectivity throughout the transaction is made, which meant that the medium was to be reserved for your transaction. Okay. Later on came packet switching. Well, I'm telling this for the benefit of the students. So, once you do the packet switching, you are able to use the medium more efficiently, which meant the cost of the medium has come down. Now, the cost of the media has come down, but the point is that what about the endpoints? Essentially, you need to have your network interface cards at both ends. So, one at the switch, one at your PC or whatever. So, once you have that, your problem would be solved. But even in packet switch network, we had HDLCs and SDLCs, which were very, very expensive. The real breakthrough came when Robert McCulloch came with Ethernet. Okay, the endpoints became very, very cheap, and also Ethernet is based on the probabilistic transmission of data, which meant that you could really cater to a very large number of users. Okay, that's how the cost came down. Look, now the hardware has become cheaper. Fair enough. What do you do with that? Now, later on, Internet Engineering Task Force came out with the different protocols. TCP/IP became a real standard in the sense that when once you have standard, technology grows. So, and then DNS was created, and then of course this was the contribution by that, which meant that you could get connected from anywhere to anywhere. So ubiquitous computing was in place. But then it also meant that you can get connected from anywhere to anywhere in the world. The use had remained quite esoteric in nature. The scientific institutes used to use for transferring their files or do some FTPs or emails and all. But then real breakthrough came in when World Wide Web was discovered by Edison and HTML was created. This did something dramatic. See, actually the file transfers were in place. Essentially you are transferring some content. But then you could also do transmission of your pictures, video, but you had a standard definition, which meant the business community saw an opportunity here in terms of the advertisements. That's where they pumped in a lot of money. So later on came XML, which really isolated the content from the header. Means more and more data could be transferred much more efficiently, which meant that you had better and better applications. So more money came in and Internet took off in 1993. An extension to this is grid computing. Okay, this is how we have progressed from the improvements in network to the grids. But let's see how the applications have changed because of this network. Initially, all your computers were connected using the typical RS-232 lines, 232C lines, which meant it had a distance limitation of about 100 feet depending on the frequency at which you operate, which also meant that everybody had to come to a fancy place called computer center to use the computer. But then telephones were in existence, so by the use of modems, you could always extend the access points to a remote location, be it across countries or across continents. So you had the remote access there. Later on, you had the lease line concept, wherein it was expensive, but then very high-end applications like running your stock exchanges, they could be done using these tandem machines, so it was used for fault tolerance. Telnet FTP were anyway there. Later on, because network was available in, it was quite cheap, so many programming paradigms have come in. First thing was the client server concept that we'll talk about a little bit. Essentially what you need to do was to initiate a program on a server and then transfer your data and your job got executed on the server. And then you have the remote execution in the sense that you transferred your code onto an external on a remote machine and then the job got executed there. Okay, an extension to this itself has become grid computing with much more fancy stuff attached to it. And then you have code on demand in the sense that for interactive applications you got the code downloaded from somewhere else and then you ran on the local machines wherein you had much better interaction, or typically for the graphical interactions you had. And mobile agents in the sense that you transferred partially executed code all over well under the control of a source machine. Okay. Now an extension to this concept has come about as grid computing. So instead of just doing content delivery and bit of computation, why not do something more? That is what grid computing is all about. Well, in an analogy, all that you need, insofar as your electrical socket is concerned, all that you are going to do is you plug your device. You don't care from where you are going to get your electrical power from, be it a thermal power station or a hydel power station or a nuclear power station. You really don't care. In grid also, you just have a laptop running a browser. All that you need to do is just submit your job requirements to a resource broker, and then it's the job of the resource broker to find the matchmaking or do the matchmaking and find the resources that meet your requirements and present it virtually for you, and then your job would be executed and the result would be staged back. So this is what the concept of grid computing is all about. Well, it appears to be same as the web, but then it allows much more. So in short, you can think grid computing as a higher level of abstraction compared to internet. In internet, when you get some information, you really don't care from where you are getting. So you do a search on your Google or Yahoo, you don't really know from which server you are being sourced from. Similarly, grid computing allows you to use the computation. You don't really have to care from where it is being serviced. Okay. Then it appears to be same as cluster computing, but then it's a lot more different because you need to have different administrative domains there. And then it does virtualization, but it does much more than virtualization in terms of resources, storage devices, computation, data storage, equipment, what have you. Anyway, I'll just go through this. They appear to be same because you'll find some boxes stacked one above the other. But the major difference is that it belongs to different administrative domain. So in grid you have different administrative domain and there's no owner, meaning you don't have to trust anybody, which also means that you need to have right security put in place. Essentially this is done using the transfer of or the exchange of the digital certificates. Okay. Other things are quite straightforward, and the very important point to be noted here is that essentially the cluster is geared towards improving the throughput of a system, but then grid really cares about improving the throughput of a job. We see from another perspective, we have seen how it looks from the processor perspective, from a network perspective, but then if you're going to see, much before I was born, there was something called mainframe computers, wherein you had many jobs submitted onto a given system. Okay. Now, later on, the processor first came down at around 1980s, and then you had one processor to a given job. Essentially, if you are a protein crystallographer, all that you need is a processor, some storage, some visualization, and then access to a protein data bank. Your job is done. So all that you needed was bundled into a single box, and that was called a workstation. This happened because the cost of the processors came down. Okay. Later on, people realized that, okay, instead of you can do your job, but then if at all you really want to do a simulation of a process or study a phenomenon, all that you need to do will be, you need to solve the partial differential equations. Okay. All your partial differential equations will come to a standard form called Ax equal to b, where A and B are huge matrices. If at all you want to solve these huge matrices, you need to have huge vector computers. Okay. You should be able to have the vector computers, but then what do you do with the data? This data should be visualized on a machine, which were typically called as graphics engines. They do only 4x4 matrix multiplication, meaning for solving you need a different kind of computation, and then for visualizing you need something else. So you need two types of computation for solving a single job, which came to be known as a client-server computing. Later on, all the functionalities of your vector processors or your graphics engines, everything were put into a commodity processor. So thereby you had a large number of systems for a given job. So this came to be known as parallel processing. And then, of course, this is a part of evolution. You cannot just throw away because you just acquire a parallel machine. You would be needing a specialized machine for the specialized purposes also. So if you can see everything as a single entity, that is called grid computing. Well, in grid computing we always say that, okay, you need to share. What is the big deal? Anyway, we are sharing your processor, your memory, your hard disk using an operating system. Operating system itself is geared up for sharing all the resources. Then what is the difference? Can we see some light if you go with this perspective? Okay. Earlier you had the centralized operating system, meaning if at all you wanted to have 10 accounts on your 10 different machines and you wanted to use multiple processors, you need to have accounts on 10 different machines. Okay. Later on came the concept of network operating system, wherein you are able to just plug in as and when you need it by the network, which meant that the number of accounts that you needed to create were less, and also you could share your spaces more efficiently amongst the different users. So later on came in distributed operating system, where everything was fed in as a service, in the sense that you had a server farm, you had a directory service, you have got a file transfer service, and then so you really never knew on which machine you were logged in. Okay, the typical examples of this were Amoeba and then Cambridge operating system. Okay, so later a much more advanced version of this would be great. In distributed operating system, you just run the microkernels on different workstations, and then you have a server there, and then in grid you are going to operate at a macro level. So this is what you are going to see. I will not go into the details of it. The point is that you need to use better security mechanisms here. What did we gain? From moving to the central operating system to network, you gain flexibility. From network to distributing, you gain transparency. And from distributed to grid, you gain dynamism, in the sense that the resource can come in and go according to a given policy. Well, we saw many approaches. All of them are correct. The point is that it looks like, it reminds me of a fable wherein 6 blind men try to figure out how the elephant really looked like. Somebody said it looked like a tree. Somebody said it was a wall. It was a rope or a spear or a fan or a snake. All of them are correct. Now, what is the classical definition given by Ian Foster? So, it should not have any centralized administrative control. It should be based on standard open and general protocols, and then it should provide a minimum quality. So, it's a much decent definition. Only thing is you are going to bind it at the runtime. Essentially, grid provides you the virtualization of many kinds, and also it helps you to share and locate your application platform to data banks, and then you are going to share the machines. So essentially, all that you need to do is to have your own local data. Everything will be found and presented to you. This is what grid computing is all about. You are going to have, it enables fruitful coexistence of all the technologies. Only thing is you have a resource broker, and then you will be able to map onto this resource which is actually satisfying all your resource requirements. Well, as you know, this has become the high-tech science, if you like, or the front-end science has become very competitive, and also you need lots and lots of resources, be it huge equipment. I will show you one of them which is very huge. Then you need to have huge data sets to work on, visualization system, computers, whatnot. So, if you really work in isolation, you are nowhere. The point is that science has become mega science, and then your laboratory will have to be a collaboratory. You may be having all kinds of money on earth, but you cannot get all experts in one place. Okay? So, you need to collaborate and then share by respecting each other's administrative policies. That is what grid computing is all about. We'll see, then what is the application on grid computing? Let's assume that you have got a program which will just take the input as the name of a person and then age, and then predicts how he would look like. At about 15 years, I have taken permission from this guy. So 15 years he looks something like this. At around 30 he is like this. At around 45 he is like this. And if you give accidentally minus 10,000, he would be like this. Like if you believe in Darwin's theory. He also believes in incarnation, reincarnation. He would do something like this after 10,000 years. So, point to be noted here is that you are going to use the same program on different data sets. Okay. This is what all the scientists do, and then they call it with a fancy name called parametric sweep. Okay. Essentially, you are going to have the same program working on different data sets. You really don't care where the result is brought from. This is a killer application on grid which really helps you to solve your problems by utilizing the resources available on the participating machines on the grid. There are many applications. First thing is distributed supercomputing, which we use for ab initio molecular dynamic computations. Essentially, it provides a large CPU and memory. High throughput, if you want to break your code, maybe your public and private key, that you need cryptography, and then on demand for extremely costly equipment that I will show you one. You will be able to share on demand, in the sense that because of grid you will be able to share these expensive equipments, and then you will be able to do your computation or your analysis. And data intensive grids, you are going to generate huge amount of data. We will talk about this, and then how is it you are going to do. This is a large hadron collider grid, and then collaborative experiments, in the sense that you should be able to do your computation You do your experiments, computation, analysis, inferencing, everything by collaborating with your fellow scientists. So this is what grid computing is all about. The point to be asked is, why is it you're going to spend money on high performance computing or grid computing? What is it in store for us? Not going into the details, most of you already know, but then the point is that numerical weather prediction, it appears to be a very mundane topic, but the point is that you need to solve continuity equations in mass, momentum, energy, and then specific humidity to solve this, which are nonlinear partial differential equations, need huge amount of computation time. Okay, and of course, if you want to realize how the materials in the earth behave inside deep in earth, you need to, because under high pressure, materials behave in a different manner. Magnetic material research, new periodic table. The point is that you have got superclusters. So all of you know about carbon 60, but then the point is why only carbon 60? There can be many more. So what is felt is that probably you will be having a new periodic table, maybe 20 years down the line, having different properties of the superatoms. And of course, national security is one, that will not talk about it. And then creating energy efficient systems. See, the best known converter of solar energy is chlorophyll. Okay, there is research in simulating how chlorophyll really works and then converts. Somebody can model that. It will be very, very nice. For that, you need very huge computation power. And also we know that 15% of all our energy is consumed by internal combustion engines. But then can we make it something better? Now, we are going to have material research. I forgot about this, very interesting. You have got many material scientists here. So, you have got some material called silicon nitride. Silicon nitride is very, very soft, but then if you just add a layer of lanthanum, it becomes extremely hard. Point is, why silicon nitride? Why lanthanum? Why not something else? So, there is huge amount of research that is required, and also there is huge amount of excitement in this. We will talk about some of the projects which we are contributing in. A Large Hadron Collider is basically we are going to have a tunnel. There is a tunnel between in the periphery of Switzerland and France, it's around 27 kilometers, and then it's something like this. So you have got this tunnel. What you are going to do here is to accelerate protons. Okay, you are going to do the proton-proton collision, and then you are going to observe. Are you going to get a new material from this? Okay. Everybody is hoping to find something called Higgs boson. But then, if somebody says with conviction that Higgs boson signatures exist and they are able to prove, well, let's say it's a very big candidate for Nobel Prize. But then scientists are secretly hoping, instead of Higgs bosons, there can be many, many, many more particles or materials or signatures to reanalyze from, because there is a lot at stake. I was talking about the equipment. So if you can see, there is a huge equipment wherein you are going to have superconducting magnets, and then you are going to cool it by superfluid helium at 1.9 degree K. This is at Sun. I was telling about the equipment. If you can just see, this fellow is a 6'4" guy, and that's the detector you have. This is what is being done at Sun. You are just going to make heavy particles collide and then try to observe for the signatures of any new particle. We are going to get data from different parts, and what is it we are doing? This is we are going to generate petabytes of data in the operation of this experiment, and then you need to analyze. There are different tiers. There is a tier structure. Tier 0 and 1 is at Geneva, and then there are around 20 tier 2 centers. 2 of them are in India. One is at TIFR Mumbai, other one is at VECC Kolkata. There you are going to get the process data, and then you have got many different centers. So tier 0, tier 1, tier 2 centers are there, wherein you are going to analyze this data. It's an open experiment. Everybody is welcome to use that. It is predicted that you will be needing around 50,000 CPUs to do a single computation by 2010. Anyway, LHC is operational from the past 9 months. What is we are doing is that we are designing, developing, and then deploying software for LHC grid, in the sense that which you need to even predict the quality of service. Supposing you submit a job to a given cluster, what is the quality of service you are going to get, what is the availability, and then all the monitoring stuff we are doing here, and then we are helping in analyzing. Okay, this is being used If anybody is interested, you can just, it's online, http gridview7.ch, gridview, it's developed by us. And then we are contributing in developing the software for a huge fabric that is present at CERN in collaboration with IT division CERN. Now, how is it you are going to access to this information? First thing is, India is coming out with what is known as National Knowledge Network, wherein all the state capitals will be having a typical network operation center. Basically, we will be having a point of presence. So, the network operation center will be at Delhi and one is at Hyderabad, for the simple reason that they lie in different seismic zones. Okay. So, should something happen to Delhi, Hyderabad would take over. Okay. Now, each of these centers, each of these points of presence would be connected by at least two national long distance service providers. It's already operational. Around 70 institutes are connected over this, and most of the IITs or the mentor IITs, they are already bringing their lectures to the IITs being mentored. For instance, IIT Kanpur does it for Jodhpur, IIT Hyderabad, IIT Madras does it for IIT Hyderabad, and then IIT Bombay does it for IIT Gandhinagar. So, for controlled classroom it's being used. Anyway, this is a typical setup we have at our institute. You may be wondering, why is it you need such huge bandwidth? After all, you are going to transmit a lecture, because National Knowledge Networks provide you with 1 gigabit, which will be upgraded to 10 gigabit bandwidth. Now, the point to be noted here is that if somebody is giving, let's say, a language talk, all that you need to do is just to focus the camera on the lecturer and then forget it. The point is, if you want to capture the niceties of interaction between the student and then carry it out to a remote classroom, and then the interaction with the students and the professor, and also why across the classroom, even in the same classroom, if you want to carry out a not so kind professor throwing a piece of chalk at a student to discipline him. So, if you want to make it more and more real, you need to have some arrangement like this, which we have at BRC Mumbai. So, you have multiple cameras, and then you will be able to carry almost realistic images or realism onto a remote site. Okay.
Now go to the electron beam center at Har Ghar, Navi Mumbai.
I just am demonstrating just a remote image that I can.
नवी मुंबई स्थित इलेक्ट्रॉन बीम सेंटर में आपका स्वागत है। बीआरसी और समीर के सहकार्य से बना ये 10 MeV लाइनैक प्रणाली उद्योग और विकास कार्यों के लिए पूरी तरह से तैयार है। हम सबकी ओर से मैं माननीय प्रधानमंत्री जी से इस सुविधा का उद्घाटन करने का निवेदन करता हूँ। Prime Minister for opening 6 new facilities of.
Well, as was stated, this was inaugurated by the Prime Minister's residence last year. At 6 facilities at BRC. One was at Kalpakam, which is around 2,000 kilometers. BRC, hence incidentally happens to be 1,200 kilometers from Delhi. And then the point I am trying to make over here is that by the pressing of the button, what you are going to do is to do something, inaugurate something remotely. This is exactly you do while conducting experiments. Okay, you do send control systems, you control an equipment, and then you collect the data, analyze them. So this is what exactly has been extended to this. This is a 6-ton facility available at Grenoble, France, which can be used by sitting at BARC, Mumbai. Okay, this is available for all the protein crystallographers. They can use send their crystals, and then automatically it will be placed by a robot here that you will be able to control, and then you will be able to do your experiments. Okay. So the idea is that you will be able to do the experiments, you will be able to do the information processing, consult with your experts, and then make some inferences, get their feedback. And the beauty of this is you are going to get the provenance in the sense that the repeatability of an experiment. So these are automatically annotated and kept. When you do an experiment, everything is kept annotated automatically. So if somebody wants to recreate the same thing after 10 years or 15 years, probably because if you have the same kind of experiments, you would still be having the facility which can be, you can recreate the whole thing because you have got the connectivity, you have got the data transfer capability, and then you will validate the results, and then you can go ahead instead of repeating the whole thing over and over again. These are some of the results which have been published using that. This is another one wherein we design what are known as fast breeder reactor components, but then the expertise is available at BRC Mumbai, IGCAR Kalpakam, and then we have got VECC Kolkata. We have got experts in different fields operating on different parts of the design of the FPTR components. So I am not very sure you are able to see here. This is the video picture of these, and they can interact with each other and then just find out whether even the plan elevation and then side view that you are going to get is proper or otherwise. That's being done. Well, what is the future of grid? The point is we really refrain from drawing any forecast because we were pleasantly surprised, because if you see the growth of computers, the IBM chief himself had predicted there would be no market for more than 5 computers, but then here we are with billions of computers which are there. And then of course even internet technology, it took almost 15 years to really mature. I remember when we were at CERN 15 years ago, people were pleading to just use it. You just use once, give your feedback. Okay. Now it's almost becomes such that you really can't live without internet. Okay. These technologies sometimes they really dramatically grow. So what we hope and believe is that grid is going to be the same way, wherein there are already many production grids wherein people are able to do their research work. Essentially grid is an enabler of utilities in the sense that it cannot do anything on its own, but then it enables the interaction between the human beings, the machines in a much more productive way. So what we believe is that grid is going to make the research much more interesting, much more transparent, and then it will be great to work with it. As we are from the Department of Atomic Energy, we hold this man in very high respect. What he said was, computers are incredibly fast, accurate, and stupid. Human beings are incredibly slow, inaccurate, and brilliant. Together they are powerful beyond imagination. What basically grid does is, by virtualizing things, it brings the human beings and the machines together, and we like to believe that in days to come, discoveries which are beyond our imagination are going to happen with the use of this technology. Thank you very much for your kind attention.